A uniformly charged ring of radius 10 centimeters has a total charge of 75 microcoulombs. Find the electric field on the axis of the ring at 1 centimeter, 5 centimeters, 30 centimeters, and 100 centimeters from the center of the ring. Now, first of all, let us organize our information. So let me denote A to be the radius of 10 centimeter, capital Q, 75 microcoulombs, and B, the distance from the center of the ring of 1, 5, 30, 100 centimeters. Right away, we can extrapolate that because Q is a positive number, that the electric field, or rather Q is positive, the electric field, the direction of the electric field would be away from the element, which in this case is the charged ring. So whenever you see a question that has a positive Q, right away you know that the electric field would be pointing away from whatever the element it will be. So let me put here at one side so that you will remember. Okay, so let us draw a visual aid to help us understand better about the question. So let me draw a charge ring with a radius of A, in this case is 10 centimeters, and with a distance from the center of the ring of B, which ends at point P. It's just an arbitrary point that ends after a distance B. You can name it anything you want. Okay, so to solve this question, we first have to understand that we need to break down Q into small elements of Q, which is infinitesimally small, in this case dq, here. Now dq is all over the ring, is the charge, the total charge of the ring, broken down into smaller elements and smaller elements. Okay, now Q would contribute to the electric field E. So it would make sense that dq would contribute dE. Okay? Now remember that because Q is positive, the field will be pointing away from the element, the charged ring. So whenever we draw, it would be away. And the hypotenuse here would be d of E. And from observation, we can see that d of E is made up of two components, dE of x and dE of y. So because d of q exists all over the ring infinitely, we can also draw another dq here that also contributes dE, that is also made out of dE of y and dE of x. Now, some of you may notice that because they are symmetrical about the axis, the dE of y at the top and bottom would cancel out each other, which results in just dE of y would be negated. So we can say that dE of x will be the only thing that's left if we integrate it together. If we summation all of the dq's together, the only thing left would be dE of x, which is why it has become our main focal point. So if we integrate around the ring dE of x, we would get our answer of E. Pretty simple. Now, how do we find dE of x? The answer lies in right angle triangles. So we can put dE as our hypotenuse, and it's made up of E of x, dE of y. So we can do the same here because this is exactly the same triangle. And we can say that these are the same angles. Okay, so we want to focus and isolate dE of x. So how do we do it? Through the use of cosine. So cosine theta is adjacent over hypotenuse, which is dE of x over dE. So right away, some of you might notice that if I want just dE of x, let me just multiply it by dE. Okay? So let me change it to a different color. And we can get our relation that if I integrate this, which is equals to this, I get this. Pretty interesting. Now, because they are the same theta, they share the same theta, we know that this is adjacent over hypotenuse, which is equals to, this is our adjacent, this is our hypotenuse, which is b over the hypotenuse. Now, in this case, distance between here and here, we call it r, the distance of dq and p. So let's change it to r. Okay, so this is one of the reasons why we don't write radius as r, just in case we are confused by the radius terminology that we use here and the r for the distance between dq and p. Okay, so another formula to take note of is E is equals to the Coulomb's constant, Q over R squared. So if I want to change it into dE, it will be dQ over R squared. Okay? So let's just plug in our formula. Times this. So this comes from here, which is this. This would be here, which is B over R. So we can take away the constants, which is E over B R cubed dQ. Now, when we integrate dq, we get the big Q because it's the summation of all the small q's, the infinitesimally small q's together. So we'll get a big Q. Okay? So, and because we have different points of B, we will need to do this multiple times. So we know that if R is the hypotenuse, then R would be a squared plus b squared root, right? So R cubed would be this. So let me write down our variables again. cm, remember? Okay. Q 6 charge. Now K of E would be 8.99 times 10 to the power of 9. Okay, so all we have to do is to plug it into this formula. So let me do the first one, and you can try out the rest on your own. The answer will be down in the description. So let me choose 1 cm would be equals to 0.01 meters. Meter. So E, so point now let me do R cube. EQ and it works out to be 6.64 times 6. So the SI unit the center of the ring. Okay, so this is important because it denotes the direction. Okay, so you can work out the rest. Just sub in different forms of B that you see here, and you can check your answers below. Thank you.